we will continue seeing Ampere's law. Now we will see the derivation of why the closed loop integral of the magnetic field dot dl is equal to the magnetic permeability times the current, I would say penetrating, as Professor Walter Lewin says, instead of enclosed. So here we have a circular conductor. We have the magnetic field in a wire. If this is a circular conductor with the wire, the magnetic field is around like this. So this is the magnetic field, or like this. If we take just a piece, for example, this piece, this piece. Let's take a quarter of the cycle. So it is like this, more or less. This is a conductor, so we have current that is inside or penetrating. So here we would have current. It is not the same to have a current here that is outside, that would be not penetrating. For example, the current being here, for example, if the conductor be here and we wanted to calculate the magnetic field here, that is different. Here we are calculating the magnetic field in this conductor. So the current is penetrating this conductor or the attached surface that we will define. So we need to calculate the closed loop integral of B dot dl. So we can divide this quarter cycle in this part. So we will have the integral of B1. Let's say this is you could say this is B1. So B1 dot dl sub 1. So this would be dl sub 1 plus B2. This would be B2, and again here would be dl. So here, sorry, in the first, in B1, we have dl going in this direction, and the magnetic field, as you know, is in this direction, because this is the magnetic field. So exactly at this position, we have this that is in between this and this. So then we have B2 that goes from here to here. Actually, let me mark A, B, C, D. So from A to B, then from B to C, of B2 dot dl, dl2 plus, oh well, use dl, B, oh well, the magnetic field, I need to put this, from C to D, from C to D, here dot dl. So here, this is the direction of the magnetic field, and this is the direction of the L, plus from D to A of B dot dl. So we know that the magnetic field around this conductor, or this cycle conductor, as we saw in the previous video, is magnetic field is equal to mu naught times the current divided by 2 pi times the radius, let me say r. So here we have dot product. So the dot product means taking the cosine of theta. So actually, if you see in this, from C to D and from A to B, dl, the vector, dl, and the magnetic field are perpendicular. So cosine of 90 degrees would be 0. So I can cancel this one from A to B and from C to D. And I just have this 2. So here I have, let's say that the the current, or the source of the current, because here I have this cycle. Well, it is not so drawn to scale, but here I have it. So I have this part from B to C, and the other that is from D to A. So they are different. Here we have, let's say, R, could be R1, and here we have R2. So here we have magnetic field. Here we need to take R1, and for this one, from D to A, we need to take R2. So the closed loop integral of B dot dl is equal to, here we have B is mu naught I divided by 2 by R1. And what is the L? We're integrating over all this. This. We're integrating over all this. Now, what is this? This is the arc length. This arc length is R1 times theta. Theta means from here to here. So theta 1. So we have R1 times theta. Here we have again mu naught I divided by 2 by R2, and this arc length we are advancing the same degree, so theta is the same, times R2 now, so R2 theta. And about these signs, here we have the magnetic field goes in this direction. You could call this positive direction or whatever you want. And the magnetic field here is going in the other direction. So here you have this direction and this direction, so they are opposite. So you need to put the negative sign, could be here or could be here. So we have that the R cancel, and actually we have that in this case we have 0. This is the magnetic field of a current that is not being or of a surface that is not being penetrated. Here I just put it to complete this cycle, but this is the case, like this as I drawn it, like this. This, and we have the current here. So this surface is not being penetrated by the current. So when this happens, the magnetic field will be 0, because here the penetrating current is 0. So in the previous video we saw why this or where does this formula came from, and now we use this formula and exactly the same approach to see why the magnetic field that is outside a current, or if we create a surface and the surface is not penetrated by that current, the magnetic field would be 0. And it's the same as with this formula. If the current penetrating is 0, the magnetic field would be 0.